looks like? All I have to do is just label that as the x-axis. Okay? If this is the x-axis, so the lobes are situated and symmetric about the axis they're on. So the piece of x is situated about the x-axis, the piece of y about the y-axis, and the piece of z is situated about the z-axis. Well then, wait a second, then what does this p sublevel look like? Well, if you put all of them together, that's what p sublevel looks like. In your packet, if you flip over to page 13, at the top you can see I'm showing you the piece of x, the piece of y, and the piece of z. And if we superimpose them all together, we get a p sublevel. I got a better picture here. I'll show you. And I'll pass this around a minute. You're going to see the piece of x, the piece of y, and piece of z. And if I superimpose all of them, that's what a p sublevel actually looks like. It looks like sort of like a bumpy sphere. Okay, so piece of x, piece of y, piece of z, and that's what the p sublevel actually looks like. Again, piece of x, piece of y, piece of z, superimpose them all together, that's what one p sublevel looks like. So p sublevel is not spherical, it looks sort of like a bumpy sphere. Questions at all? So far so good? Okay, so we go out to that third energy level, third building, which has 3 floors. We go into the first floor, one giant room, one orbital, and s orbital. We go to the second floor, and sure enough, like any other second floor we've run into, it has 3 rooms. It has 3 orbitals that make it up. It has a piece of x, a piece of y, and a piece of z. Oh, before I move any further, let me point something out. You'll notice that the piece of x, piece of y, and piece of z, on average, belonging to that same sublevel, they're all the same distance from the nucleus on average, right? So, if we were to compare a 2p means a second energy level, p sublevel. If I want to specify the orbital, I can call this the 2p sub x. The 2p sub y orbital would be a different orbital belonging to the same sublevel. Orbitals belonging to the same sublevel are said to be degenerate. Okay, the word degenerate, if someone says you're a degenerate, they're not paying you a compliment, okay? That has a different connotation. But here, the word degenerate means equal in energy. Orbitals that belong to the same sublevel are said to be degenerate, which is simply another way of saying that they're equal in energy. So an electron belonging to the 2p sub x and an electron belonging to the 2p sub y would have the same exact amount of energy, even though they were in separate orbitals. And that's because they belong to orbitals of the same sublevel in the same energy level. Questions? Okay, so we come back to this third energy level, this third building, which has its first floor, its S sublevel, which has one room, the S orbital. We go to the second floor, the second sublevel, the P sublevel, with it has the piece of x, piece of y, and piece of z. This time it's the 3 piece of x, the 3 piece of y, and 3 piece sub z, because we're in the third energy level. If we go to the third floor, which is our third sublevel, that's script L equaling 2. Remember, it's counterintuitive. You would think it's a third sublevel, so it should be 3, but it's not. It's 1 less. It's 2. In other words, what we call the D sublevel, it turns out, guess how many rooms are in that floor? 5. See the pattern? 1, 3, 5. There are 5 orbitals. So I'll separate those again using hatch marks. We have the script M sub L value equaling -2, -1, 0, +1, and +2. Remember, the M sub values go from whatever L is, negative, to the positive form of that L. So since we're dealing with the D sublevel, where L equals 2, our M sub L values go from -2 all the way to +2. Now, we have names for these. This is the dx, well, I don't know if I want to make sure you do. Yeah, why not? This is the dx. Okay, I'm going to make a deal with you. You have to know the letter names, but you don't have to know which letter names go with which numbers. Fair enough? So everyone in here should know m sub l equaling -1 is the p sub x. It goes alphabetically, sort of goes from negative to positive, alphabetically x up through z. So it's not hard to see. Okay, x is -1, y is 0, z, that's the +1. You guys with me so far? All right. When I was taught the d values and the subscripts and how they match up with the m sub l values, it changed from when I was in school to what we use today. I don't know. It could change again. All that told me when I saw that it changed is because it's pretty arbitrary. It really is. It's kind of just whatever we adopt by convention. So I'm not going to make you match it up. You have to know the m sub l values for d go from -2 to +2, and you have to know the letter names, but you don't have to know which one matches up with which. Fair enough? Okay. All right. So we're dealing with the following. This is the dxy, this is the dyz, excuse me, xz, this is the dz squared, the dyz, and the dx squared minus y squared. If you want to try to remember the names, I'm going to put them in a different order, okay? Because that's how it matches up, but I'm going to put them in a different order so it's easier to remember them. Just remember it this way, go alphabetical. So dxy, dxz, dyz, dx squared minus y squared, and the dz squared. See what I'm saying? It's easier to remember it in that. That's how I learned it, okay? And that's how it used to be matched up. Now they put the z's toward the center, and the x and y's are on the outside. So it's just a little less counterintuitive, I think, in terms of trying to learn what those letters are. I don't expect you to be able to match up the m sub l value with the proper letter name, but I do want you to know the letter names. Now, these rooms have a different shape. That is, the orbitals are a different shape than the p orbitals or the s orbitals. And there's more than one type of shape. It turns out, of these 5 orbitals, 4 of them are 4-lobed. And 1 of them is 2-lobed with a torus, a donut. Okay, torus, T-O-R-U-S, is the geometric shape you're familiar with, what some of you would call a donut. Okay, so let me show you what it looks like. So 4 of them are 4-lobed. It's easy to know which ones are the 4 that are 4-lobed. The ones that have 4 lobes are the ones that specify 2 axes. The one that is the weird one, the 2-lobed with the donut, that's the dz squared. Now, it works a little bit differently than on the p sublevel. In this case, the axes specify where the lobes are located. If you're dealing with squared, they're on the axes. If they're not squared, they're between those axes. So for instance, a dxy, okay? To show the dxy, I just need to draw two axes, the x and the y. I'll label it. And then because this is not squared, it tells me that the 4 lobes are not on those axes, but between them. So this is what it would look like. That's a d sub xy orbital. Dx squared, here, you want to see the dyz? Here, let me show you the dyz. Ready? Watch. Watch. There you go. Now, I don't expect you to be able to draw 3-dimensionally. So I don't expect you to be able to draw the x, y, z coordinates and then somehow, I mean, God, I wouldn't want to have to do that. I mean, I don't have the artistic skill. I would be there too long trying to do it. So if I ask you this, all you have to do is just draw the axes, and I don't care which one you call it which. It really is kind of up to you. Okay, yeah. Yeah, if you want to put the z-axis here and you want to put the y-axis there, that's fine with me too. All right, now, the dx squared minus y squared, because these are squared, this tells us I'm dealing with the x and the y, but this time the lobes are on those axes. So this would be the dx squared minus y squared with the 4 lobes all situated about those axes. The dz squared, that's the weird one I was talking about. This is the one, this is my z-axis. This is the one that is 2 lobes, so it looks kind of like a p orbital, but it has a torus. That's one orbital. Well, how's it, wait a second. How's the electron get from over here to over there? Well, remember, all this is simply, all we're trying to show here is the region of space where we have a high probability of finding an electron. Well, how does it do that? Well, the theory doesn't address that. Okay, I mean, you have to remember too, the electron can behave as a wave, so it can move in a wave-like fashion to get from one place to another. All we're doing is specifying where we're most likely to find the electron. We're not actually trying to talk about how it moves. If you actually talk about the path of electron as an individual particle, you could argue it moves in a fractal pattern. You guys done fractals? What?
Isn't it the thing that has like an infinite perimeter?
Yes. Yeah. Right. That would be a way, and it gets sort of kind of weird. I actually have a picture of the d orbitals drawn in 3D and drawn and sketched out so that they're actually arranged in the axes the way that you would see them. So not what I would make you do, but this is actually right here. And you'll notice that as I look at this, they don't show you what the d sublevel looks like. So here are the 5 d orbitals. Okay, the dxy, dxz, dyz, and the dx squared minus y squared, and the dz squared. Here's all 5 of them situated in space relative to the x, y, and z axis. Do you see how they did take all 3 of them and superimpose them to show you what a d sublevel is, like they did up here? Because what would it look like? Just like a bumpy sphere, right? I mean, this looks like a bumpy sphere already. This would look like even more like a sphere that has bumps on it outside of it. Are you okay with this? Good. So again, these are the d orbitals situated about, if we put them all together, we would get a d sublevel. And maybe it's probably a good idea right now to draw the atom now as we understand it. So let's do that. Let's do that. I'll put it up over here. We know we have the first energy level, right? Here's our nucleus. First energy level, S sublevel. First energy level has an S sublevel, 1 orbital, an S orbital. It's spherical. There, I've drawn it. Now, the second energy level consists of 2 sublevels. There's the S sublevel with its 1 S orbital. I've drawn it. And now the P sublevel with its 3 p orbitals, which are arranged in space 90 degrees from one another along the x, y, z axis. So we have the 2p sub x orbital, the 2p sub y orbital, and the 2p sub z orbital, all making up the 2p sublevel. Now we have the third energy level. The third energy level consists of the 3s sublevel with its 3s orbital. It has the 3p sub x, the 3p sub y, the 3p sub z, and then it has the 5d orbitals that make up the third energy level. Can you see how this is going to start to look like a spiral? You guys know what a spirograph is? Yeah, those of you who play with the spirograph. Yeah, do you see how it's going to start looking like? I mean, it's going to look, it might look sort of interesting and artistic, but it's going to be nonsensical in terms of trying to be able to look at that and really see anything meaningful. You guys understand? This is why we represent it this way. This doesn't give you a true reflection of how it actually looks, but it does show you, hey, these orbitals are degenerate, they're all equal in energy, the electrons belonging to them are all about the same distance on average from the nucleus. It's useful, and it shows you how the energy lines up from sublevel to sublevel. We good? If we go to the 4th building with its 4 floors, its 4 sublevels, we go to the S sublevel, the P sublevel, the D sublevel, and what's the 4th sublevel called? Level-wise? The F sublevel. The F sublevel, guess how many orbitals make it up? 7 orbitals. Okay, 7 orbitals. Of those 7 orbitals, we have the Fz cubed, the Fy cubed, the Fx cubed, the Fxyz, the fz times the quantity x squared minus y squared, the fy times the quantity z squared minus x squared, and the fx, of course, minus the quantity z squared minus y squared. I do not